Hello Matrix and welcome to Was a Matrix. My name is Looney and I'll be assisting you to get all of your questions through to us. Today we're doing your final exam prep for maths. All you need to do is search us on all the social media platforms, Was a Matrix, as well as hit us up on our WhatsApp line. Don't forget guys, we've got a cool competition going on for you, so do stay tuned to get all of those details. I've got Nicolene, our sign language interpreter, with me, as well as our awesome teacher, Nicola. Thank you so much, guys, and over to you.
Thank you so much, Looney. And welcome to all the Matrix. This is your final exam preparation for Maths Paper 2. Today we're going to hopefully cover some analytical geometry, some trig, and then at the end we're going to try and do some Euclidean geometry. So we've got a lot to get through, so let's get started. Okay, we're going to start with some analytical geometry, and we're told that we have, in the diagram, we have C, which is the center of a circle defined by x squared minus 6x plus y squared minus 4y plus 9 is equal to 0. We can see that's our circle over there with center C. And then we have point T, has the coordinates minus 1y, and it's a point outside the circle. And we have two tangents which are drawn to the circle from T. So there's T over there. And then we have that tangent over there. And we have this tangent over here. So this tangent goes to point A on the circle and that tangent to point B. Okay, so we're told that STB is a tangent to the circle at B and has the equation y equals minus 2x plus k, whereas TA is a tangent to the circle at A and is parallel to the x-axis. And finally, we're told that BV is a diameter of the circle. So that's this line over here, diameter, which goes through the center. All right, so the first question is we're asked to determine the coordinates of C. So just to remind you, point C is the center of the circle. And we have the equation of the circle. But in order to be able to extract the coordinates of the center and, of course, the radius of the circle, we need to rearrange this by completing the square and getting it in the form of x minus a squared plus y minus b squared is equal to r squared. And when we have it in this form, then the center of the circle is the point with coordinates a, b. All right, so let's do some of that algebraic manipulation. So we have x squared minus 6x. The constant that we need to add to x squared minus 6x is plus 9. To turn it into a trinomial, that's a perfect square. Then we have plus y squared minus 4y. And the constant we need to add to those two terms is plus 4. To turn that into a trinomial, that is a perfect square. I'm now going to put all the constants on the other side. First, I'm going to start by taking this plus 9 to the other side, which becomes minus 9. And then, of course, I'm going to add the plus 9 and the plus 4 that I added to the left-hand side to create those perfect squares. So I'm now going to factorize each of these trinomials. This is going to become x minus 3 squared. This trinomial is going to become y minus 2 squared. And on the right-hand side, this simplifies to 4. And from here, I can now extract the coordinates of that center. So C now has the coordinates 3, 2, which I get from there and there. And although it hasn't asked me for the radius, I can see from here that the radius squared is equal to 4, which means that the radius is equal to 2. Okay, so C has the coordinates 3, 2. All right, let's go to the next question. The next question is determine the equation of BV. All right, so BV is this diameter over here, and we know that it now goes through the center of the circle, which has the coordinates 3, 2. So that's really important. We're going to use what we figured out in part 1 or part A in this question. And so it's going to go, we're going to use each bit of information we get probably in the next question or the next section. Okay, so to find the equation of that line, we need two things. We need the gradient of the line, and we need the coordinates of a point on the line. So we have the coordinates of a point, and that's point C, which obviously lies on the line. how can we get the gradient of the line? If you look carefully, B is obviously the point of intersection between the tangent and this radius over here. And our circle geometry tells us that the tangent is always perpendicular to the radius. And we're also told what the gradient of this straight line is. This line's gradient is -2. So therefore, the gradient of BV is perpendicular to the line SB. So therefore, their gradients, the product of their gradients, must be equal to -1. So the gradient of line BV times -2, which is the gradient of line SB, must be equal to -1. And therefore, we know that the gradient of line BV is equal to 1/2. And always just take a moment to think about whether it makes sense. We expect BV to have a positive gradient, and it does. Okay, so it's 1/2. Now, the last thing we need to do is we need to find the equation of that line. So we're going to use our equation formula. Y minus y1 is equal to m into x minus x1, where m is the gradient and x1, y1 is are the coordinates of a point. So we can now substitute those in. We know that y minus 2, got the 2 from that over there, is equal to 1/2 into x minus 3. I'm just going to neaten that up so that I have y equals. So I'm going to have y is equal to 1/2 x minus 3 over 2 plus 2. And finally, y is equal to 1/2 x plus 1/2. So minus 1.5 plus 2 gives me plus 1/2. Okay, so that is the equation of this line over here, BV. All right, let's move on and see what the next question is. The next question asks us to determine the equation of line TA. Okay, so TA is this line over here. Now, we were told that TA is a tangent, and we were also told that it is parallel to the x-axis, and we really need that information to be able to find the equation of this line. So any line that's parallel to the x-axis is always going to have an equation of form y equals c, where c is the y-intercept, okay, or the point where that line cuts the y-axis. So again, we're coming back to this point C, which has the coordinates 2, 3. And we also know that the radius of the circle is equal to 2. So there's actually quite a few radii drawn here. There's a diameter over there, and there's this radius over here, AC. And we know that that is 2 units. So we are already 2 units up when we get to point C, because we have, we are 3 units up when we get to point C, because we have the y coordinate of 3. And now we go another 2 units up from that, so we're going to be at 5. So therefore, this line cuts the y-axis at 5 units, and we can therefore say that the equation of the line for TA, the equation is therefore y equals 5. Okay. All right, we now have to calculate the length of TB. Okay, so, and we have to give reasons. This is really important. Okay, so TB is that line segment over there. And we can see that it is the length between point T, which is the point outside the circle, and point B, which is where the tangent meets the radius or the diameter. And we know that, of course, this line over here is going to be equal to that line over there. Why? Because the tangents from the same point outside the circle will always be equal to each other. So, can we calculate the length of this line over here? So we know that it is -1, the x-coordinate of this point is -1. And we also know that the x-coordinate of this point is 2. So therefore, we know that the distance between those 2 points over there, -1 to 2, gives 3 units. So if this line TA is equal to 3 units, then this line TB must also be equal to 3 units. So TB is equal to TA, which is equal to 3 units. And our reason is that they are tangents from the same point, that point being point T. Okay. All right, we've got the same diagram. Okay, let's determine the value of K. K is the y-intercept of that line, y equals minus 2x plus k. Okay, so we have the gradient of that line being minus 2, and the value of k is going to be the value of the y-intercept, as I said. Okay, so in order to find that, we need to know the coordinates of another point on that line. And luckily, we do have the coordinates of another point on the line. It's this point T, and we now know that the x-coordinate is minus 1, and the y-coordinate, if you remember, this line is 3 plus 2, which is 5 units up. So therefore, this point has the coordinates minus 1, 5. And I can substitute those two values into this equation to find the value of k. So when x is equal to negative 1, and this is on line S or TB, let's call it TB, on line TB, when x is equal to 1, y is equal to 5. So I'm now going to substitute those into this equation. So therefore, 5 is equal to minus 2 times minus 1 plus k. So we have 5 is equal to minus 2 times minus 1 is 2 plus k. Therefore, k must be equal to 3. Therefore, the equation of this line is y equals minus 2x plus 3. And now we've found that value of k. All right. And the last question is that we need to calculate the value of angle ACB. Okay, so let's go and look at this diagram. Okay, so angle ACB is this angle over here. It's that reflex angle. Okay, well, it's actually an obtuse angle. It's not actually a reflex angle. So how are we going to find the size of that angle over there? Usually, when we're looking at angles in analytical geometry, we're going to be using our gradient formula. And our gradient formula tells us that tan of the angle that a line makes to the x-axis is equal to the gradient of that line. So there's quite a few ways that we could actually probably find that angle. I mean, it would be possible to say, find the size of that angle over there, and then subtract that from 180 degrees to get angle ACB. But a more efficient way to be able to calculate the size of this angle is to look very carefully at this quadrilateral over here. You can see there it is. So it's quadrilateral ATBC. And if we understand our circle geometry, we can see that that is a cyclic quadrilateral. And the reason it is cyclic is because those two angles over there are both equal to 90 degrees. They're both the angle between the tangent and the radius, which means they're both right angles. And of course, when we have a quadrilateral that has an opposite pair of angles being supplementary or adding up to 180 degrees, we know that the quadrilateral is cyclic. And the reason that's useful is because the exterior angle of a cyclic quadrilateral, which is this angle over here, the exterior angle of the cyclic quadrilateral is always equal to the opposite interior angle. So in other words, if we can find the size of this angle over here, angle STA, then we have effectively found the size of this angle over here, which is angle ACB. And luckily, this angle happens to lie between the positive x-axis, or I should say a line that is parallel to the positive x-axis, and this line over here. Okay, and I know that the gradient is equal to -2. So I'm going to call this angle theta over here, and I'm now going to use this little formula which tells me about the relationship between the gradient of the line and the angle of inclination of that line. So I'm going to say that tan of theta is equal to -2. And therefore, that angle theta is equal to the inverse tan of -2. Right, time for the calculator. Pull that out. Okay, so we're going to find inverse tan of -2 and close our bracket. And that gives us an angle of -63.43 degrees. So obviously we don't want the negative version, we want the positive version. So we're going to add 180 degrees to that. And we get the angle as being 116.6 degrees. Okay, so therefore it is equal to 116.6 degrees. And if this angle theta is equal to 116.6 degrees, then this angle over here must also be equal to 116.6 degrees. And again, your reason would be that we have the exterior angle of a cyclic quadrilateral. Okay, so that's it for this segment. In the next segment, we'll be looking at some trig, which is one of my absolute favorites, very exciting. And otherwise, I'll hand back to Luni.
Thank you, Nicola. Guys, let's take a quick break and we'll see you shortly after this. Welcome back from the break, guys. If you've just joined us, we are doing your final exam prep to help you with the upcoming exams. If you're constantly running out of data, then this next competition is just for you. Wazometrics is bringing you the hashtag WazoWinner competition, where 2 lucky matriculants stand a chance to win 2 gigs of data. All you need to do to enter is head on over to our Facebook page and all of the details will be there. Thank you so much, Nicola, and over to you.
Thanks so much, Luni. All right, let's get going with some trig, as I said, one of my favorites. Okay, so we're going to start with question 2, and it's a proving an identity question, which is something that a lot of people struggle with. Okay, let's read it. It says, prove the following identity. So we need to prove that cos squared x minus cos x minus sine squared x all over 2 sine x cos x plus sine x. We need to prove that that is equal to 1 over tan x minus 1 over sine x. Okay, always with proving identities, really one of the most important things to remember is that you cannot assume that the left-hand side is equal to the right-hand side in order to prove that the left-hand side is equal to the right-hand side. So you really need to remember to break it up. Okay, so we have a left-hand side over here, and we have a right-hand side over here. And what we need to do is we need to work with the left-hand side, and we need to try and use our identities and various definitions to turn the left-hand side into the right-hand side. Okay, so let's start with that. I'm going to start with the left-hand side. Okay, so we know that when we do trig identities, we're going to be using a lot of very common skills and tools. We might be using factorizing, we might be using multiplying out, those sort of things. We might have to add and subtract fractions. So let's see what tools we need to use here. In the numerator, we have cos squared x minus cos x minus sine squared x. All right, so just be careful here. You don't have cos squared x plus sine squared x, so you can't use that identity. But hopefully you know from your double angle formulas that cos squared x minus sine squared x is equal to cos of 2x. All right, that's not going to be very useful though, because if I change that into cos of 2x, the numerator is going to become cos of 2x minus cos of x. And the reason that's not useful is because I can't really work with ratios when they have different angles. So let's try and bring that cos of 2x back into a cos of x by rewriting the cos of 2x as 2 cos squared x minus 1. All right, and that's going to be a lot more helpful, because then what we're going to have is an expression in the numerator that we're actually going to be able to factorize. And we're going to see how it all comes together from that. Okay, so we're going to write, I shouldn't have erased that. So the left-hand side, this and this is now going to become 2 cos squared x minus 1. And then, of course, don't forget the minus cos x over there. Okay, let's turn our attention to that denominator. In the denominator, we could possibly turn that into a sine of 2x, but again, that's not going to be useful because then I'm going to have a 2x and an x, they're different angles, all in the same denominator, and I can't work with different angles like that. So rather, I'm going to try the approach of factorizing. I'm going to factorize a sine x out of there, and I'm going to be left with 2 cos x plus 1. All right, if I look at that numerator now, I now have a quadratic expression, a quadratic trigonometric expression. And I can factorize that into 2 cos x plus 1 and cos x minus 1. And that's all over sine of x times 2 cos x plus 1. Okay, so remember, all I did to go from there to there was factorize that quadratic expression. Okay, and very beautifully now, I can cancel that factor with that factor over there. And that leaves me, just going to come onto the side over here. I'm just going to erase that. So very, very beautifully, once those have cancelled, I'm going to have cos x in the numerator, cos x minus 1, and of course I have my sine x in the denominator. I can break that numerator up and put each part over the sine x. So I've got cos x over sine x minus 1 over sine x. And the last thing I need to do is convert this into a 1 over tan x. Remember that tan x is equal to sine x over cos x. So therefore, 1 over tan x is it's the reciprocal of that. It's going to be cos over sine. So this can now be simplified to 1 over tan x. And then, of course, I've got my minus 1 over sine x over there. All right, and therefore, I've now proved that the left-hand side is equal to the right-hand side. Okay, let's move on to a general solution equation. You will always get a general solution trig equation in any paper too, so it's really important that you focus and understand what we do here. Okay, so I've got 4 plus 7 cos theta plus cos of 2 theta is equal to 0. Now, as I mentioned in the last question when we were doing the identity, I can't work with different angles over there. So I'm going to have to take this double angle and I'm going to have to convert the cos of 2 theta into a more usable ratio. So always with cos of 2 theta, you've got your 3 options, the 3 different formulas that you'll have on your formula sheet. I'm going to again use the fact that cos of 2 theta is equal to 2 cos squared theta minus 1. And the reason I'm using this particular equation is that I'm going to have cos of theta, and that's going to leave me with an equation in only cos of theta. So this is going to become 4 plus 7 cos theta plus, and this I'm now going to write as 2 cos squared theta minus 1, and that's all equal to 0. Okay, let me just simplify. The 4 minus 1 gives me 3, so we can see that I now have a quadratic equation. So 2 cos squared theta plus 7 cos theta, and I have plus 3, and that's all equal to 0. I can now factorize this expression. I'm just going to use my little cross on the side here. That's what I like to do. Maybe I'll just do it up here. So I've got a 2 and a 1, and the factors of 3. I've got a 3 and a 1 over there, and they're both positive. So I can see that my factors are 2 cos theta plus 1, and my other factor is cos of theta plus 3, and that's equal to 0. So now I've got the product of 2 factors being equal to 0, which means that one of those factors must be equal to 0. So therefore, cos of theta must be equal to -1/2, or cos of theta must be equal to -3. So let's just look at that solution. Okay, so we know that cos of theta never goes above 1 or below -1. So if we just remember what the function looks like that. So it starts at 1 and it goes down to -1. So there's no value of theta that is going to make cos of theta equal to -3. So there's no solution from this particular equation. So this is no solution. No value of theta is going to make cos of theta equal to -3 because it never goes below -1. So I need to focus all my attention onto this part of the general solution, and I'm going to do that on the next page. So I know that cos of theta is equal to -1/2. So I'm going to get my reference angle first. My reference angle is the inverse cos of 1/2. For your reference angle, you're always going to use a positive number over here. And that, hopefully you know, it's a special angle, is equal to 60 degrees. Now I have to decide which quadrants I'm in to get my values of theta. So I'm going to use my cast diagram, and I can see that cos, so I want the two quadrants where cos is negative. And cos is negative in quadrant 2 and quadrant 3. So those are the two quadrants that I'm going to have my solutions. So in quadrant 2, I'm going to say that theta is equal to, now in quadrant 2, I've got 180 minus theta. So it's going to be 180 minus 60 degrees, and that's plus K360 always, with sine and cos, it's your K360. So therefore, theta is equal to 120 degrees plus K360. And the final part of my solution is going to be my quadrant 3 solution. So in quadrant 3, I'm always 180 plus theta in quadrant 3. So therefore, my solution is going to be equal to 180 plus 60 degrees plus K360. And that is equal to 240 degrees plus K360. Okay, so you were asked for the general solution for that question, so you don't have to substitute any integers into K to find the more specific solutions. You can keep it in that form as the general solution, and you can see you have an infinite number of solutions. Okay, so that's it for this segment of the trig. In the final segment, we're going to be doing a bit of Euclidean geometry. So back to you, Luni.
Thank you so much. Guys, we are going to take a quick break, but before we do, don't forget to send us your questions, your comments. Let us know how the exam prep is going so that we can assist you as best as we can. We do have that competition as well, so please enter so that you can stand yourself a chance to win data. Don't go anywhere, Matrix. We'll see you straight after this. Welcome back from the break, Matrix. I hope you guys are still enjoying the lesson. Thank you so much, Nicola, and over to you.
Thanks so much, Luni. All right, so let's get going with the last segment. We're going to be doing a 3D trig question, and then we'll do a little bit of Euclidean geometry. Okay, so this is the 3D trig question, and we're told that points L, M, and N are in the same horizontal plane. Don't forget, this is horizontal, that's vertical. And KL is a vertical tower. All right, so let's have a look at that diagram. So you really need to kind of like zone in on it and imagine that this is sticking out. There's your L, N, M in your horizontal plane, and this is the vertical tower over there. Okay, we're told that NLM, first, the angle of elevation of K from M is Q degrees. Angle NLM is P degrees, NL is equal to NM is equal to D, and KL is equal to H, and I think that's all on the diagram. Okay, so we can see our various angles. That's P over there, that's D. Okay, those are equal, so that's also D, and that's angle Q over there. Yeah, I think that's it. Okay, so the first thing we're asked to do is to determine the size of angle LNM in terms of P. Right, so angle LNM is this angle over here, and this often comes up that we have an isosceles triangle, especially when we need to use the sine rule in trig. Okay, so we're going to focus our attention on this triangle over here, which is on the horizontal plane, and it's triangle LMN. Okay, so we know one of the angles in that triangle. In fact, to help us understand, I'm going to draw the triangle over here. I'm going to remove it from the diagram and draw it outside. So we have LNM. We know that this is angle P, and we know that those two sides are equal. So effectively, we're working in an isosceles triangle. Because it's isosceles, we know that this angle is also equal to P degrees. And the angle that we're trying to find the size of is that angle over there. So we know that the three angles together, so angle LNM, which is the angle we're trying to find, plus this P, plus another P, so plus 2P, is equal to 180 degrees. And that is because the sum of the angles in a triangle is always 180 degrees. So therefore, LNM is equal to 180 degrees minus 2p. Okay, so not too bad. Okay, so the next question asks us to prove that Lm is equal to d times sine of 2p over sine of p. Okay, so what we've just found is that this angle over here is equal to 180 degrees minus 2p. And we're trying to get the length of this side over here, Lm, and we're trying to get it in terms of d and p. So we're going to use the sine rule, and the reason we're going to use the sine rule is because we have the angle opposite the side we're looking for, and we also have the angle opposite d, which is equal to p. Okay, so we're going to use the sine rule in that triangle. So I'm going to say that Lm over sine of the angle opposite it, which is 180 minus 2p, that is equal to side d over the sine of angle p. All right, so sine of 180 minus any angle is always just the same as sine of that angle. So I can reduce that to just sine of 2p. So therefore, Lm over sine of 2p is equal to d over sine p. And the last thing I'm going to do is multiply both sides by sine of 2p in order to get rid of that denominator on the left-hand side. So therefore, Lm is equal to d times sine of 2p all over sine of p. Okay. And now the last part of the question asks us to show that h is equal to 2d times cos of p times tan of q. Okay, so when you see the word hence, it always means that you're going to use the information in the previous question in this question, or in the previous part in this part. Okay, so looking at what h is, h was the length of that tower. So KL is equal to h. So KL is a length of this triangle over here, and this is actually a right-angled triangle. And in this right-angled triangle, we know that we have angle Q. Again, I'm just going to draw the triangle over here. So right-angled triangle, we have H over there, we have angle Q over there, and then we have LM down here. And if you remember, we've just found, or just written LM as being d times sine of 2p all over p. And the really great thing about this question is we're in a right-angled triangle, so we can just use our trig ratios as they are. We don't need to use area rule or cos rule or anything like that. We can just go ahead and use one of the ratios. So if we look relative to side q, we're working with the side opposite, and we're working with the side adjacent to it. So therefore, we're using our tan ratio. We're going to find what tan of q is. And we can therefore say that tan of q is equal to the side opposite, which is h, over this adjacent side, which from the last question we know is equal to d times sine of 2p all over sine of p. Okay, so let's just finish it off on the next slide. So we know that therefore h is equal to tan of angle Q times, and the reason we're multiplying is if we go back, we need to multiply both sides of the equation by this denominator. And that way we're going to isolate the h, and we're going to bring this over to the other side. Okay, so we have tan of Q times d times sine of 2p all over sine of p. And the last thing we need to do here to make this expression look like we want it to look with a cos is we need to rewrite the sine of 2p as 2 sine of p times cos of p. Okay, so therefore h is equal to tan of Q times d times 2 sine p cos p all over sine p. And those sine p's then cancel, so finally we can say therefore h is equal to 2d, 2 times d times tan of Q, there it is, times cos of p. Okay, so the last question, which is our Euclidean geometry, we're given some information about our diagram. Okay, there's our diagram. Let's read what we need to know about it. So we're told that O is the center of the circle. We're also told that PQRS is a cyclic quadrilateral. And then we have the tangent through P intersects line RS produced at A. Okay, so we have center, we have our cyclic quadrilateral, we have our tangents, and the last bit of information is that OB is perpendicular to PR and that PA is perpendicular to AS. All right, so that's all in our diagram over there. And the first question is that we want to prove that triangle APS, which is this, APS is this triangle over here. We want to prove that it is similar to triangle BRS. So BRS is this triangle over here. So we don't have any information about the sides of these triangles, so we're going to have to prove the similarity using the fact that they're equiangular. So that's what we're trying to show, that they're equiangular. And we know that each triangle has a right angle, so that's really good news, makes our lives a bit easier. We also know that this angle over here, P4, according to the tan chord theorem, is equal to that angle R1 over there. And then because the sum of the angles in both triangles is 180 degrees, this angle over here, oh, let me use my blue, this angle over here must be equal to this angle over here. So I'm going to write that all nice and neatly now. Always in geometry, you're aiming for neatness and logic. Okay. All right, so I've got in triangle PAS and triangle RBS, and don't forget to link the angles. So the angles must match when you write the triangles out like that. Okay, so I've got angle A is equal to angle B2 is equal to 90 degrees, and that's given. I know that angle P4 in my blue triangle is equal to angle R1 in my purple triangle, and that's because of the tan chord theorem tells me that. So therefore angle S1 in my blue triangle must be equal to angle S3 in my purple triangle, and the reason for that is the sum of the angles in the triangle, in both triangles, is 180 degrees. Therefore triangle PAS is similar to triangle RBS, and the reason is that they're equiangular. So you can say AAA, some people like to write the angles out like that, and either is absolutely fine. Okay, and then the last question that we're going to do today is that we need to prove that AP times RS is equal to BR times PS. So if we look at what we've just proved, we've proved that triangle APS is similar to triangle, sorry, I'm just going to go back here, BRS. Okay, and when you're using your similarity to find these to find the product of the sides, you can always just use your little rainbows to link the corresponding sides together. So AP in the one triangle links with BR in the other triangle, and PS in the one triangle links with RS in the other triangle. So therefore you know that AP in this triangle over BR in this triangle, so remember AP links with BR, must be equal to PS in the first triangle over RS in the second triangle. Again, those two link. So use your rainbows to link the sides together like that. It's really useful. Okay, and then all we need to do is multiply both sides by RS first. Okay, and then we can also multiply both sides by BR. So effectively, we're just eliminating both of those denominators there. So the BR cancels with that on the left. And then finally, we have RS times AP is equal to PS times BR, which is exactly what we were asked to prove. All right, so that's the end of the revision for paper 2. I really hope it's been useful and that you've been able to learn a few things about geometry and trig. I wish you all the best for your exams. Don't stay up too late, rather get an early night's sleep and get some rest. Maybe do a little bit more revision, and good luck for your final exam. Okay, over to you, Luni.
Thank you, Nicola. Guys, it's been a great show. I hope you enjoyed it and you took as much information as you can to help you prepare for your exams. Everything of the best, and if you have any questions and comments, remember to send those through and we'll assist you as much as we can. Congratulations to all of our competition winners who will be announced on our Facebook page after the show. For more revision, please visit our website on www.wazametrics.co.za, and if you missed any of the shows, they are available on our YouTube channel. Well then, from me, Luni, Nicoline and Nicola, thank you and goodbye.
Wazametrics 2021 Catch-Up is brought to you by the Department of Basic Education, NECT, ETDP SETA, SABC, MultiChoice, and DBE TV on OpenView Channel 122 in partnership with